Okay, so let's do some numbers. A parallel RLC circuit. See what this looks like. Okay, I'm going to use the example from the handout. What's available, it's under the PowerPoint listing on Blackboard. These are the same numbers on every example and every lesson along the way. So we have an inductor with 80 millihenries, capacitor 50 microfarads, installed in a parallel circuit with a resistance of 10 ohms, powered by 120 volts at 60 hertz. So all the same numbers as before. So first of all, the voltage. So voltage is constant because it's a parallel circuit, 120 volts. Now, we're given the sizes of the loads, so we have the impedances, okay, which kind of looks like we need to deal with the impedance triangle, but remember it's all the inverse values, so we would really rather not. So let's see if we can avoid that. So I'm going to start by listing these. We have R equals 10 ohms, okay, and I've done the math to calculate for XL and XC. Let me see where those numbers, so XL equals 30.16 ohms. That's a number that we've calculated before in many of these examples, as well as XC, okay, which is 53.03 ohms. Okay, so there's our three resistances. So when we compare XL and XC, XL is roughly 30 ohms and XC is roughly 53 ohms. So it looks like we have a more capacitive circuit, right, if we just look at the resistances. Okay, and this is where we get into trouble if we try to work within the impedance triangle. Okay, because remember, within the impedance triangle, it is the inverse values. So I've got the inverse of XL down here and the inverse of XC up here. Now, XC looks to be a bigger number, so it looks like it's capacitive. But in fact, when we compare the inverses, the bigger number becomes the smaller number. Okay, so all of that just to say, let's get away from that impedance triangle. Is there any way that we can move on? What do we have? Well, let me say this. Before I answer that question, I've got one other thought. Notice that I had not yet finished drawing the triangles, because I don't know whether the hypotenuse is going to be up here or down here. That's exactly what we're trying to figure out, right? So for the time being, I've left that entirely off. Okay? I also, let me see, I would like to call this IR. Okay? But I'm going to hold off on that because I don't know whether I want to put it above or below this vector. Okay, if the hypotenuse is here, I've got it in the right place. If the hypotenuse ends up here, then it's really in the way. I'd rather have it below. So I'm going to hold off on that too, because I really want to figure out what the triangle is going to look like. How can I do that? I know the voltage, and I know all of my impedance values. I can use Ohm's law to calculate for all of my current values, okay, which gets me over here, and then I can really start to understand the circuit, okay? So if I equals E over R, we have one version of E. We simply need to use the right version of R, okay? R, Z, XL, XC, whatever it is. So if I want to calculate for IC, so this is the current that's leading the voltage, the current through the capacitive portion of the circuit, IC equals 120 volts divided by XC. So what's XC? XC is 53.03 ohms. So I calculated that. Hit pause, grab your calculator, come on back. IC equals 2.26 amps. Okay, let's do the same thing for IL. IL equals the voltage, 120 volts, divided by XL, the inductive reactance. XL, 30.16 ohms. Hit pause. Come on back. IL equals 3.98 amps. 3.98 amps. Sorry guys, that's a little ugly. There it is. So now let's answer the question, is this an inductive or a capacitive circuit? And we can compare our currents. So we have a larger current through the inductor than we do through the capacitor, which means when we cancel these two out, because they're out of phase by 180 degrees, the resultant vector, whatever's remaining, is going to be down here. So I could draw a vector here and call this Ix. Okay? And Ix is the difference between IL and IC. So it's 3.98. Now here in terms of the math, we have to decide how to do this. It's going to be the larger number and subtract from that the smaller number. We've already decided its location. Okay, this is going to be an inductive circuit because the inductive current is a bigger number. So take that inductive current, subtract the capacitive current from it, and what are we left with? 1.72 amps. Okay, and now we can draw the vector, the hypotenuse, which is IT, and I had IR in the right place, it turns out. What is IR? It's 120 volts divided by R, 10 ohms, which is 12 amps. Okay, now we can use, we can finish our triangle. Hit pause, go and do that. Come on back. How did you finish completing your triangle? We know two sides. We can find the third side using Pythagoras, which is 12.12 amps. And then we can use, I would suggest probably tan, using the two less calculated values, but we have all three. We can use sine, cos, tan, doesn't matter. To fill in this blank, we can see by these numbers the hypotenuse is only very slightly bigger than the adjacent, which means the angle is going to be very small. And it is. It works out to be about 8 degrees. And then when we calculate the power factor, we can recognize it is going to be really close to 1. This is very nearly a resonant circuit. Okay, very nearly. Power factor equals 0.99. And here, more important than ever before, we had better identify this as leading or lagging. What did we end up with? We ended up with XL, which is pointing towards, we ended up with IX, which is pointing towards IL, meaning we ended up with an inductive circuit, meaning the power factor is lagging, because in an inductive circuit, the current lags the voltage. So we have a lagging power factor. Okay, really important here. This is an inductive circuit when it's all said and done, so we have a lagging power factor. A really high power factor, a really small angle. The reason for that is we have a really small value for resistance, which means we have a lot of current flowing through that resistance, that resistor, okay, ends up giving us a really small angle. Okay, and that's it. We don't have to go back here and fill in the impedance triangle at all, because we know our three values for impedance, the resistance and the reactance. We don't even have to bother with this triangle. And now we can move forward and fill in our power triangle. We've got all of our currents. We have our one and only voltage. So we know that the true power is equal to 120 volts times 12 amps, which is 1440 watts. The apparent power is equal to 120 volts times the 12.12 amps, just ever so slightly more, ends up being 1454 volt amps. And our two reactive powers, 271 VARs, 271 VARs on the capacitive side, and 477.6 VARs here in our inductive power vector. Okay, so there you go, guys. There are the numbers. Hopefully that helps. Go and work on the exercise sheets. Fire me off a email or some other message if you have additional questions. We need to look at this and a particular part of it a little closer.